Hello, welcome to this MATLAB video tutorial. Today's lecture is concerned with numerical integration. Numerical integration basically is a broad family of algorithms for calculating the numerical value of a definite integral. And in this video, we will introduce three of these methods: the rectangular rule, the trapezoidal rule, and Simpson's rule. So let me first start MATLAB. Today, we will work in this folder. Remember always when you start MATLAB to select the folder where you want to work. So I'll start with these three files in my folder, okay? And I want to give you a graphical illustration of how the numerical integration methods work. So I will start with this main illustration, integration rules. Okay, here I don't want you to understand all this code. I'm just using it to plot a graphical interpretation of how numerical methods work. So let me just run this part of the code. Let's say I want to compute the integral of a function f in a definite interval, let's say between a and b. So this integral graphically is the area which is under the curve defined by the function and the x-axis, and between, in this case, a would be 0 and b would be 4. Okay? Now, there are several reasons for carrying out numerical integration. One reason is that maybe we don't know f of x. Okay, maybe we don't have the analytical formula of f of x. For example, when we use sampling, when we use in the laboratory sensors to get values of the function. So embedded systems and maybe other computer applications may need numerical integration for this reason, because we don't know f of x. We don't know the formula of f of x. We just have some sampling points. Now, another reason could be that a formula for the integrand may be known. I know f of x, but it may be difficult or maybe impossible to find the analytical antiderivative, the analytical integral of this function. And finally, another case could be that maybe I can compute that antiderivative, but it's very hard to compute. That could be if it's an infinite series or product, or if its evaluation requires a very special function that is not available. Okay? So for different reasons, maybe we need to compute this in an approximated manner using numerical integration. So which methods can we use to approximate this area in an approximated fashion? Well, the first method, the first idea is this one. Let's subdivide the initial interval into more subintervals, and let's approximate the area in each of these subintervals. The main idea here is that I will subdivide in many subintervals, very small subintervals. In each one I will make an approximation. Okay? The first method is called the rectangle rule. There are three types of rectangle rule: left, right, and midpoint. Let me show you first the left rectangle rule. The main idea is in each of the subintervals I use the left value of the function to define the height of this rectangle. So in this first subinterval, the height of the rectangle is defined by the value of the function and at the left interval, at the left side of the interval. Next interval, the same idea. Let's say I'm in interval I, and I want to approximate the area in this subinterval. Okay, the left rectangle rule will evaluate the function at the left side of the interval, which is point xi, and f of xi is going to define the height of my rectangle. So I will approximate the area under the curve by the area of this rectangle, which is very easy to compute. It's the height times the value of the base, which in this case is the difference between xi plus 1 and xi. And that's the way we compute this area. Okay, fxi times h is going to be the size of the intervals. Here in this video, I'm assuming all intervals, all subintervals have the same size, are equally distant points. Okay? Now, the right rectangle is the same idea. The only difference is we will use the value of the function at the right end of the interval to define the height of the rectangle. Okay? So for example, in this rectangle I, which is defined by xi and xi plus 1, the right rectangle rule uses the value of the function at the right end of the interval. So f of xi plus 1 now defines the height of the rectangle. So this value, f of xi plus 1, times h, which is the base size of the rectangle, gives an approximation of the area. Okay? Now, the next method that we will use is the midpoint rectangle rule. Again, we will use rectangles, but now the height of the rectangle is obtained evaluating the function at the midpoint of the interval. So between xi and xi plus 1, I will compute the midpoint. It's called here x mid, and I will evaluate the function at that point. This value defines the height of my rectangle, okay? And the height times the base is going to give me the approximated area. So these are the three types of rectangle rules, depending on where we evaluate the function at the left point of the interval, at the right point of the interval, or at the midpoint. There are other methods. The trapezoidal rule, for example. In this case, the trapezoidal rule, instead of approximating the area with rectangles, it approximates the area with trapezoids. So we can see that we use the value of the function at the, let's say in this interval, we evaluate the function at this point, we evaluate the function at the other endpoint of the subinterval, and we construct the line through these 2 points. And we will compute the area of this trapezoid. So that's why it's called the trapezoidal rule. Okay? This area can be computed using this formula, f of xi plus f of xi plus 1 divided by 2 times h, which is the size of the subinterval. Okay? This will approximate the area by only the area of the trapezoid in each of the subintervals. And the last method we will study is called Simpsons Rule. In this case, Simpsons Rule will construct in each subinterval not a line like the trapezoidal rule, but a parabola that goes through these 3 values of the function. So it will use the value of the function at the left and the right ends of the subinterval, but also the value of the function at the midpoint. And it will compute the parabola that goes through these 3 points. And then it will approximate the area, computing the area under the parabola. And the area under the parabola can be computed like this, okay, using this formula. So f of xi plus 4 times f of x at the midpoint plus f of xi plus 1 divided by 6. Okay, we have 4, 5, 6 values of the function, so it's weighted coefficients. They are divided by 6 times h. Okay, so we can see in this graph that the function is better approximated using parabolas than using, for example, rectangles. Yeah. Of course, this is going to give me a better approximation of the area than this. Yeah. Here I'm not taking into account these areas. Yeah. This is a much better approximation. Yeah. Okay, so this is the main idea. Here we have the different formulas from the left, Simpson rule, and so on. So I'm not going to close these figures, figure 2, figure 3. I will keep them, okay? I can close figure 1 and also let me see, let me run it again and make sure I have all the figures I need. Okay, I want to keep the figures that explain the methods: Simpson rule, trapezoidal rule, midpoint rectangle, right rectangle, and left rectangle. But I don't need these ones. They were just used for explanation, for illustration. So I will just keep these ones. Okay, now this was just to illustrate how the method works. Now, I would like to show you this main numerical integration code. In this main file, this program will return approximations of the integral of f of x between a and b, and the left rectangle and midpoint rectangle rules are going to be used. Okay? So we start with clear all. This will clear all the variables in my workspace. This will clear the common window, and I want to use format long. I want to see all the decimals. Here I start defining a function f, which is sinus of x plus 1. I want to compute the approximated value of the integral of this function between a, in this case 0, and b, in this case 4. Now n is going to be the number of subintervals that I want to use, and I will start calling left rectangle rule. This is a function that is already given, so let's see how it works. Left rectangle rule. This function returns the approximated value of the integral in this variable, and the inputs of this function, left rectangle rule, are the mathematical function I want to compute its integral, a and b that define the definite integral, and n, which is the number of subintervals that we want to use. Okay, so if I want to write down this function, first I need to compute h. H is the size of the subintervals. So let me now show you the left rectangle rule here. Okay, and for the left rectangle rule, we need h. H is going to be the size of each of the subintervals. If I use equally spaced points, then b minus a divided by the number of subintervals is the size of each of these subintervals, that is called h. Then this variable contains the points that define the subintervals from a to b, from a to b, from a to b. They are at a distance h. Okay, so I'm defining these points, all these points 0, 1, 2, 3, 4, in this variable that is called points. So this is a vector that contains all the points that define the subintervals. Okay, now this is the output variable, and I will initialize it with value 0 because I will make a loop here, a loop over subintervals. I will start at the first subinterval and I will go up to the last subinterval, n. And at each subinterval, I will add to this variable the area of that subinterval, the approximated area in that subinterval. For example, for the left rectangle rule in interval I will compute the approximated area by f of xi, because it's the left rectangle rule, I need to evaluate the function at xi. So f of xi is the height of the rectangle times h. So I will need to add here h times f of xi. How can I know who is xi? Well, xi is stored in the vector points at position I. So here I select xi, and then I evaluate the function at this point and multiply by h, and this is the new area I have to add to the output variable. So at the final step of this loop, I will be at the final interval, and I will add the area of the last subinterval. Okay, that's how it works. Okay, so let me run this part of the code, and we'll obtain this value for the approximated integral. So in order to know if it's correct, or at least if it's close to the exact value, in MATLAB we can compute the exact area of an integral, and that can be done using this. We can compute the exact area with MATLAB using a symbolic variable called z, for example. So I define Sims z. Here I'm telling MATLAB z is going to be a symbolic variable. Now I can use this command int to compute the integral of the function f between a and b, and then I use double because I want the result with 16 decimals. Okay, so if I run this, I will get the exact value of the integral. It's still busy computing that exact value. So the exact value of the integral is 5.6. The approximated value we got was 5.7. Okay, it's quite a good approximation, taking into account that we were using just 10 intervals. Okay, of course, if we increase the number of subintervals, maybe 100, then I get a better approximation. It gets a little bit closer. Oh, sorry, I did not run the n equals 100. Sorry for that. Okay, if I use 100 points, then this gets closer to the exact solution. Okay, now let's do an exercise together. We already have the left rectangular rule given here. Okay, now I would like to code the other methods. I would like to code the right rectangle rule, the midpoint rectangle rule, trapezoidal and Simpsons rule. And I would like you to try to do it by yourself. So maybe it's a good idea if you stop the video now and then you check later if you did it correctly. Okay? Okay, so I will now code the other methods. I will start with the right rectangle rule. Okay? If I want to code the right rectangle rule, what I would do is, first, I will save this as, instead of left, I will call it right rectangle rule. So this should be called right rectangle rule. And what's the main difference now when I want to code the right rectangle rule? If I watch the figure 4, for the right rectangle rule, I need to evaluate the function at the right end of the interval, not at point xi, but at point xi plus 1. So when in this loop here, instead of using point xi, I need to use point xi plus 1. I will call this variable xi1. So I need to use the next point, point I plus 1. Let's check it. For example, for I equals 1, that means the first iteration, I will use the second point, yeah? Because the second point stored in the vector is the right end of the first interval. So that's right, yeah? So here, f of xi1 is defining the height of the rectangle times h. H is exactly, it's computed exactly the same as before. Yeah? So this is going to be the right rectangle rule. Okay, let's save it. Save. And then we can run it. Okay. Maybe we can also change this. This is the approximated integral with the right rectangle rule. I will change that everywhere else. This should be IRR, and IRR, okay? So here, IRR will contain the output of the right rectangle rule. Now I can try to run it if it works. Okay, and I get an approximated value of 5.6, yeah, similar to the exact value, yeah. As we are using quite a lot of points, we are using 100 points, okay. Okay, now let's code the mid rectangle rule. Now I will save as, and I will call this mid. Now the main difference, I have to change the name of the function here also. This is going to be the midpoint rectangle rule. So Shift Enter will change all the appearances of this variable. And now I need to, if I see the figure here, for the midpoint rule, I need to compute the midpoint between xi and xi plus 1. So I need xi, I need xi plus 1, and then I need x mid, which is the midpoint between xi and xi plus 1. And this midpoint is the one that gives me the height of the rectangle, yeah. Sorry, that's x mid, okay, times h, which is the size of the base of the rectangle. Okay, so that would compute the left end of the subinterval, the right end of the subinterval, the midpoint, and this would be the midpoint rectangle rule. So let's save it. Let's run it to make sure it's correct. Okay, we get this approximation. It looks similar to the other approximations. Great. So let's move now to the trapezoidal rule. How can we compute the trapezoidal rule? Okay. If we go here, we will save as, and then this will be called trapezoidal rule. Now this should be called trapezoidal rule. Remember, always the name of the file and the name of the function should be the same. Very important. And now we need to know how to compute this area. If we go to figure 6, which is the trapezoidal rule, we see that the area at interval I is computed this way: f of xi plus f of xi plus 1 divided by 2 times h. So we need xi, we need xi plus 1. We don't need the midpoint in this case. We don't need this point. Yeah. What we need is to evaluate the function here at xi plus fxi plus 1 and divide by 2. So is h times f of xi plus f of xi plus 1 divided by 2. Okay, very important, check your parentheses. Okay, these parentheses, okay, they are correct. So this is the trapezoidal rule. Let's check it once, trapezoidal rule. And we get this value. Okay, if we compare with the exact value, it's much closer than the other methods. Okay, you can see it's much closer. And finally, let's code Simpson's rule. Okay, code Simpson's rule. I will save as Simpson. I need to change this name of the function, very important. The name of the file and the name of the function should be the same. And now I need to check the formula to compute the area. Yeah. So if we see here figure 7, we can see that Simpson's rule formula looks like this. I need f of xi, I need f of xi plus 1, but I also need the midpoint. Okay, so I need again x midpoint, which is xi plus xi plus 1 divided by 2. And the formula here is different. Yeah, the formula here is h times this linear combination of f of x divided by 6. So h times whatever divided by 6. And inside these parentheses, I have f of xi plus 4 times f of x mid plus f of xi1. Okay, that's Simpson rule. Let's save it and let's check it's running. So for Simpson's rule, we get even a much better approximation than with trapezoidal rule. Yeah, we were in fact expecting that because, as we saw in the figures, this is a much better approximation of the shape of the function. Yeah. Okay. Now, what we can do now is we can check the error. So let's compute the error for all the approximations. Compute the error for all the approximations, so we can better check how it behaves, how the error behaves. So for example, let's compute the error for the left rectangular approximation. The error is the difference between the exact integral, which is computed here, ex, minus the approximated value given by the left rectangular rule is called ILR, okay, ILR. This will compute the error for the left rectangular approximation. And I will do the same for the right, midpoint, trapezoidal, and Simpson rules. So for the right rectangle, then for the midpoint rectangular, now for the trapezoidal rule, and finally for Simpson's rule. Okay, it's clear what we do here. I'm just computing the error for the 5 methods we have coded. Okay, in all cases, I'm just computing the exact value minus the approximated value for all the methods. Okay, so if I run this, they are pretty small. Okay, but what we can see here is that left and right rectangular have the same order of magnitude, the error. For the midpoint rule and trapezoidal rule, they have the same order of magnitude. And Simpson's rule is much precise. Yeah, we have the smallest error is given by Simpson's rule. Okay. Now I would like to increase the number of subintervals and study how the errors decrease for each method. So let me, for example, let me start with 10 intervals. Okay, n equals 10. And let me compute here what happens when we run for different values of n. Okay, let's study, let's see what happens when we increase the number of subintervals. We expect that when increasing the number of subintervals, the error will go down to 0. But let's see how fast they converge to 0. Okay? So for example, let's compute the error again for different values of n. So I need to call this for different values of n. First, I will compute with n equals 10. Then I will compute, let's say this is for n equals 10. And I will compute for twice the number of subintervals. So I will multiply by 2 the number of subintervals and see what happens here. And let's see, I don't know, if I multiply by 10, okay? Just let's see what happens if I use 100 subintervals, okay? And I will compare this. So I will compute the error for the left rectangular with 10 intervals. And I will compute this same error for 20 and 100 intervals. So for 20 and 100 subintervals. So what I'm trying to do here is I call the same method, left rectangle, with the same function, same subinterval, but with different number of subintervals. Just 10 subintervals, double number of subintervals, and 10 times more subintervals. And I want to check how the error decreases with this method, left rectangle. Okay? So I'm computing the error for this same method, but with different number of subintervals. So if I do that, we can see here that the error with 10 subintervals is this one. If I double the number of subintervals, the error approximately divides by 2. And if I multiply by 10 the number of subintervals, the error divides by 10. So that's why this method, that's why this method, left rectangle, the left rectangle is called a linear method. It is a linear method. When we multiply by 2 the number of subintervals, the error divides by 2. When we multiply by 10 the number of subintervals, the error divides by 10. The same is going to happen with the right rectangle rule. Okay? So I'm not going to do it. You can do it by yourself if you want. You must get exactly the same. It's also a linear method. But let's check what happens with the midpoint rectangle rule. Okay? So this is the left rectangle. Let me check what happens with the midpoint rectangle rule. So instead of left, I want to call the midpoint with 10, 20, and 100. Let me change this because I want to keep consistent with the notation. That should be an M, midpoint. And the same here, I want midpoint, 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 and the same here yeah, here, midpoint, midpoint, and the midpoint rule. Okay? So with the mid rectangle rule, 10, 20, and 100 subintervals, we compute the approximated integral, and we compute the errors. Let's see what happens, okay? Now we can see here when I double the number of subintervals, this is divided by 4, yeah? And when I multiply by 10, the error is divided by 100. So this is called a quadratic method. It is a quadratic method. Yeah. When I divide, or when I multiply by 2 the number of subintervals, the error is divided by 2 to the power 2. Yeah. And when I multiply by 10 the number of subintervals, the error is divided by 10 to the power 2. So that's why it's called a quadratic method. Okay? This is for the midpoint rectangle. And the same is going to happen with the trapezoidal rule. If you check trapezoidal rule, you will see exactly the same behavior. Okay? Now let's check Simpsons rule. Let's check what happens with Simpsons rule. Let's see if I use Simpsons rule. I will use here Simpson rule. So Simpson rule. Here I will have Simpson rule. Same here. This is Simpson now. Okay. So I'm using Simpson rule with different number of subintervals, 10 subintervals. What happens when I double the number of subintervals? What happens when I multiply by 10 the number of subintervals with the errors? Okay. So let's run this one. Now this is the error with 10 intervals. What happens here when I double the number of subintervals, the error is divided by, difficult to see here, let me compute it. If I compute this over this, okay, we can see how much is divided the error, yeah? Yes. So the error was divided by 16. Okay? So when I double the number of subintervals, the error is divided by 16. Okay? And what happens when I multiply by 10, so 10 times 10 is 100 intervals. What happens with the error when I multiply by 10 the number of subintervals? The error is divided by 10,000, 10 to the power 4, okay? Sorry, 10 to the power 3, 10,000, yeah? So this means Simpson's rule is a method of order 4, yeah? When I multiply by 2 the number of subintervals, the error is divided by 2 to the power 4. That's 16, yeah? And when I multiply by 10 the numbers of intervals, the error is divided by 10 to the power of 4. Yeah. So that's why this method is giving the best precision in the approximation. Yeah. Okay. Why is this important? This is important to make predictions. Yeah. Now I can, for example, make a prediction of, okay, now if I multiply by 30 the number of subintervals, how much is going to be diminished, the error? How much is going to be the error divided by? I can compute that because I know that it's a method of order 4. Yeah. So I will leave you an exercise here. Approximate the integral of x to the power of 3 between 0 and 1 using n equals 10. Compute with MATLAB the, let's say, exact value using the symbolic variables, yeah, using this, okay? And after that, with no extra computation, make a prediction of the error in the case we use n equals 20 and n equals 100 subintervals. Okay, that's an exercise for you. Okay, and with this we finish this video. See you in the next one. Bye bye.